Today, we're going to dive deep under the hood of your Android phone. We're going to explore a system you use literally every second, but probably never even think about: the binder mechanism.
So, have you ever wondered how, when you're playing a song, the title and the controls just magically appear on your lock screen? Or maybe how an app can ask the phone's GPS for your location? You see, for security, all these apps run in their own little isolated worlds. So how on earth are they communicating with each other?
Well, the answer is a really powerful and incredibly efficient system at the very heart of Android, called the binder. You can think of it as the essential secret messenger that connects every single part of the Android world. We're talking everything from your apps to the system services and even the hardware itself. Now, to really get what Binder does, we first need to understand a concept called inter-process communication, or IPC. See, for your phone to be secure, every single app runs in its own process, totally walled off from every other app. IPC is just the rulebook, the set of mechanisms that lets these isolated processes talk to each other and share data safely.
You know, a great way to think about Binder is to picture it as a super secure, incredibly fast central post office. An app packages up a message, puts an address on it for a specific system service, and then just hands it off to Binder. Binder then takes care of the delivery, all the security checks, and even gets your return receipt. It handles the whole shebang.
So, how does this post office actually work? Well, it's built on a few key components that all have to work together in this perfectly timed dance. Let's break them down.
First up, you've got the binder driver. This thing is the real heart of the system. It lives deep, deep inside the Android kernel. That's the core of the operating system that has total control over everything. The driver is the actual messenger, the one carrying the data back and forth, making sure everything runs smoothly and securely.
Okay, next we have the service manager. Now, if the binder driver is the messenger, the service manager is the master address book. When a system service, like say the location service, starts up, it registers itself with the service manager. Then when your app needs to find that service, it just asks the service manager for the right address. Simple as that.
And how is all this data packaged up for its trip? Well, it's put into something called a parcel. A parcel is just a super lightweight and really efficient container. The process of packing the data into the parcel is called marshalling. And you guessed it, unpacking it on the other side is unmarshalling. The whole thing is built from the ground up for speed.
Okay, so let's put it all together. A typical transaction follows these 5 basic steps. First, a service, like our GPS service, registers itself with the service manager. 2, your app, the client, asks the service manager, "Hey, how do I find that service?" 3, your app sends its request, all packed up nicely in a parcel. 4, the binder driver grabs that parcel and securely routes it to the right service. And finally, 5, the service does its thing and sends a response right back.
Now, this system is obviously designed to be secure and efficient, but what happens when something goes wrong? What happens when this trusted messenger gets tricked? Let's take a look at a real-world example. Okay, so what you're seeing here is what a normal, healthy binder transaction is supposed to look like. It's a really well-structured package. You've got the data itself, you've got a set of offsets, which are kind of like bookmarks telling the system where everything is, and you have security information that verifies who sent the message. It's all very clean and orderly.
But back in 2019, a major vulnerability was discovered. Its official name is CVE 2019-2181, and it was caused by a tiny but absolutely critical flaw, a little math bug called an integer overflow deep inside the binder driver. And this tiny bug could be used to tear down the entire security model.
So here's how it worked. An attacker could craft a malicious parcel, but in it, they'd claim a piece of data was way, way bigger than it actually was. This would trick the kernel's internal math, causing that integer overflow. And what's the result? The kernel would then try to copy that data to a location in memory outside of where it was supposed to go, overwriting other critical system information. This is a classic buffer overflow attack, and it's exactly how the attacker could gain control.
And this whole exploit is just a brilliant, if scary, illustration of why binder security is so important. It's not just some extra feature, it is a fundamental pillar of Android's entire security architecture. One little crack in the central messenger can cause the whole building to shake.
All right, let's switch gears a bit and look at this from a developer's point of view. Because Binder is incredibly powerful, but it has some very strict rules, especially when it comes to threading that can get you into a lot of trouble if you're not careful.
So first, you have to understand the 2 different kinds of binder calls. A synchronous call is like making a phone call. Your app makes the request and then it just waits, totally blocked until it gets an answer.
An asynchronous call is more like sending a text message. Your app fires off the request and then immediately moves on to do other things without waiting for a reply. Now that difference becomes absolutely critical when you start talking about resources. So here's the question. What happens when two different processes both need to lock a resource, like, say, access to a file, and then they both make synchronous binder calls to each other? You get what's called a classic deadlock. Let's just walk through this. Process A locks its resource, and then it calls process B. But at the same time, process B locks its own resource and calls process A. See the problem? Process A is now totally blocked, waiting for B to finish. But B can't finish because it's stuck waiting for A. They are permanently, completely stuck.
So the most crucial point here, and this is the official advice from the Android Open Source Project, is simple and it is absolute. You do not hold any locks when you are making a binder call. Period. That is the golden rule for preventing these nightmare deadlock scenarios.
Okay, so we've been deep in the technical details, the mechanics, the potential pitfalls. Let's pull back now and look at the big picture, just to really appreciate why Binder is so fundamental to the entire Android experience. So why does Android go to all this trouble to use Binder? Well, it comes down to three huge advantages. First, security. It automatically checks the ID of every single app making a request, so there's never any doubt about who is asking for what. Second, performance. It's built to be blazing fast, minimizing how many times data has to be copied around in memory. And third, a unified API. It gives the entire system one consistent language to talk, from the simplest app to the deepest parts of the hardware. When it comes right down to it, Binder is the glue. It's what connects the apps you use every day to all the system services running in the background. It even bridges the gap to the software that talks directly to your phone's physical camera, its GPS, and all its other sensors. It ties everything together.
And hey, just to give you a sense of its scale, every single service on your phone has a pool of 15 threads just standing by, ready and waiting to handle incoming Binder requests at a moment's notice. The whole system is built from the ground up to be responsive.
So really, Binder is Android's invisible nervous system, constantly firing off messages to coordinate every single thing that happens on your device. And that kind of leaves us with a final thought, right? What other complex, absolutely fundamental technologies like this are out there, hiding in plain sight, powering the devices we all use every single day?